Hey everyone, so today we are starting chapter 4 and we are starting with section 4.2, which is about area. To work on this, we first need to practice with something called sigma notation, and basically you can use that to write out complicated sums. And then we'll talk about how we can use sums to approximate the area of a plain region, not a place. Okay, I'll fix that for your notes. So, first of all, what is sigma notation? So, sigma notation is this notation that you see here, where there's this thing that kind of looks like a capital E. It's the Greek letter sigma. And so what's going on here is we have the sum of n terms. So this is a way to represent a sum. And if you have never seen this before, then it will make some more sense when we do some examples. But basically what this means is I is the index of the summation. This, whatever is down here, is your lower bound. The n is your upper bound, so that's where you're going to stop. And then you'll have some sort of term in there. So what this is saying right now is this is saying we would take a sub 1 plus a2 plus a3. And so this is the first term, the second term, the third term, all the way up to the nth term, which is where you stop. So let's practice. In this example, we're going to convert these sums into sigma notation. So first start off by drawing the sigma. And then in example A, notice we're just adding integers. So it's just integers versus in B, it's like the integers being squared. So here I see that I'm starting with 4 and I'm ending with 8. So I'm going to say my lower bound I equals 4. At the top, you don't put I equals, you just put the number where you're stopping. We're stopping at 8. And this would just be I. Like we're not doing anything to those numbers. So this would mean start at 4. So you replace that I with a 4, then you replace it with a 5, then a 6, then a 7, then an 8, and you add them together. For B, it's a little bit different. We have each of these terms being squared. So what's different is instead of just an I here, I'm going to put an I squared. And my first term is a 1 because I'm starting with a 1 squared and I'm ending with a 6 squared. And oops, not a 6 squared. That would take forever. We're ending with a 6. Okay, so that's how you write something. That's how you can convert a sum into sigma notation. And now we're going to practice taking sigma notation and writing it as a sum. So for this first one, we have we're starting at 1, we're ending at 5, and the expression is I minus 8. So we're going to start with a 1 minus 8. And we're going to add that to a 2 minus 8. We're going to add that to a 3 minus 8. And we're going to add that to a 4 minus 8. And we're going to add that to a 5 minus 8. And then we're going to stop because we wanted to stop at 5. That was the upper bound. And then you can find each of these and add them up. I guess let's do that. So this is negative 7. This is negative 6, negative 5, negative 4, negative 3. And if you add those, we get, let's see, 10, 10, 5. So this is going to be negative 25. For the next one, you would definitely use the calculator. So I won't actually add it because I forgot to do it earlier, but we'll write out what the sum would look like. So here, instead of an I, we have a K. Sometimes you'll see a K, sometimes you'll see an I. You could technically pick whatever letter you want. So here we're going to start. Notice the lower bound is 3, so we're going to start with 1 over 3. Then we're going to add 1 over 4, then 1 over 5, 1 over 6, 1 over 7, 1 over 8, and then stop because 8 was the upper bound. And so that equals something, okay? Use the calculator. Okay, so there are properties of summation and some summation formulas. And so the first two here are the properties, and then the rest are formulas. So anywhere you see a k, that's a constant. That is representing a constant. So let's see what this is saying. So this is saying that if you have a constant, you can move it out front of the sum, so you don't have to keep it in the sum. If you have a constant being multiplied by your term, you can move it out front and then do the multiplication at the end. If you have a sum or a difference, you can split that up into two sums and then add those together or subtract them. If you have a sum of a constant, so let's say you had like from I equals 1 to 3 of 5, this is basically saying that you're gonna, the first term is 5, the second term is still 5, and the third term is still 5. And so here we're ending up with 3 5s, which is 15. But so see how it ends up being your n times your k, 3 times 5 if you have a constant. And then these ones are like pretty nice to know because they'll save you time. So instead of having to sit there and add up like we did here in A, that could take a really long time, especially if that number got big. So this is where the properties can really come in handy. So let's practice. For the first one, I have my I see, and I have a constant 4 being multiplied. So I'm going to bring that 4 out in front of my sum. And so now what this is saying is we have 4 times that sum starting at 1 and going to 8. And so you could certainly write it out 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8. But maybe you don't feel like doing that. And so to make it faster, what you can do is you can use the property. And so in this case, we would be using property 4, as you can see that that matches this setup. And so that's saying we can set that equal to, we can rewrite that as n, and in this case, n is 8. So this would be 8 times 8 plus 1, that's 9, divided by 2. And so you could do this instead of having to add up a bunch of numbers. And I think that ends up being 144, hopefully. Okay, is that right? You guys check it. Okay, this one, so I see I have a few things going on. I have a sum, so I'm going to first deal with that sum. So let's break this up into two sigma notations. Now I have a 3i. I'm going to bring the 3 out front. I'll just have my I. And then here we have the constant, which is just a 2, right? So that means we're starting at 1, going to 5, but they're all 2s. 2 plus 2 plus 2 plus 2, so 5 times. So it just is 2 times 5. So this ends up being 2 times 5. That's from property 3. And then for this first term here, we're using the formula 4 again. So we're going to have a 3 out front, and then we're going to have 5 times 6 over 2 plus 10. And let's see, 5 times 6 is 30. 30 divided by 2 is 15. 15 times 3, 45 plus 10 is 55. So that's what we get for that one. And then for C, you're going to see one or two like this in the homework. And in the homework, it'll say for n equals 10, 100, and 1000. Now for the notes, we're only going to do it for 10. But I want you to see the purpose here. I'm not going to just replace the n with a 10 because then you'd have to do the problem kind of like 3 times. So I'm going to leave the n as it is and then substitute at the very end. So it's going to make it easier. But notice that the n is a constant, right? The n is going to be a constant term. It's either going to be a 10 or a 100 or a 1000. So I can pull out the 1 over n squared. And then I'll have I plus 1 left in here. And then I can break that up a little bit more. So of I, and then from I equals 1 to n of 1. And I should put brackets around this because that 1 over n squared will need to be multiplied to the whole thing. And now we're going to use some formulas again. So we're seeing number 4 show up once more. So this part here, this first one is going to be n times the quantity n plus 1 over 2. Still have my 1 over n squared. And then here we're just adding up 1 n times. And so remember this property 3 ends up being k times n, which is 1 times n, which is n. And then I would make a common denominator here. So that would be 2n over 2. And then I would distribute that. So I see I'm getting n squared plus n, and then I have plus 2n. And so now I'm going to have, so n squared plus n plus 2n is going to be n squared plus 3n over 2. Now we can multiply these. We get n squared plus 3n all over 2n squared. And then you can factor out an n in the numerator, simplify that with the denominator, and you end up with n plus 3 over 2n. And then this is where you would plug in your 10, your 100, your 1000. Just makes it so you don't have to do the whole problem multiple times. So save it, leave the n, and then substitute at the end. And so here n is 10, so we're going to do 10 plus 3, 13 over 20. Okay, and now this is kind of the main part of the lesson. So this is the next big fundamental question of calculus, is how do we find the area of a region that is bounded by functions? So the area under a curve. And so to do this, we are going to take our interval, whatever interval we're working with, a to b, and we are going to divide it into n sub-intervals. And we want them to all be of the same size for the purposes of today. And so when you do that, you get this formula. So the delta x here is representing the width of your intervals. Okay, so here we have some images drawn, and you can see there's kind of like 2 different ways to do it. You can over approximate or you can under approximate. And then the more sub-intervals you have, so in these ones we have 4, in these ones we have more than that. 1, 2, 3, 4, 5, 6, 7, we have 8. Notice that it gets better the more and more intervals you have. Your approximation gets better because here we're missing some pretty big chunks, but here it's a bit smaller. Okay. what is this all about? So these are called either circumscribed rectangles or inscribed rectangles. And so circumscribed ones are when the area of the rectangles ends up being greater than the area of the region that you're trying to find. And so when you add up, so the sum of the areas of the rectangles is called an upper sum because it's an overestimation. And this is a formula for the upper sum. Now, you really don't have to like write it like this, but this is the actual formula. And all that this is saying, because I know it looks a little scary. So what this is saying is that you have the sum, right, from I equals 1 to n, where n is the number, remember, n is the number of subintervals you have. So all that this is saying is if you add up the areas of the rectangles, you get this sum. That's all it's saying, right? Because this is the width of the rectangle, because that's the size of the rectangle. And then this is the maximum value of the function in that particular subinterval. So, for example, if I look at this one here, now one of my subintervals was 1.5 to 2, and the maximum value on that interval, so this would be the minimum, and then it's increasing. This would be the maximum value on that interval. So this is saying if you find what that y value is, so you do f of that value, you end up with the height of your rectangle. Whoa. Okay, that wasn't supposed to be an arrow. This thing does crazy things sometimes. Okay, so that's the height. So this is representing the height of the rectangle. And then the other one is the width. And so it's just saying if you add them all together, you'll have your sum. Similarly, you have the inscribed rectangles. And the difference here is that it's a lower sum and that you're working with the minimum value on the interval. So again, here we have this minimum value was the one that was chosen for the height rather than on the left side you see the maximum value was chosen for the height. Okay, so we are going to practice. We're just doing one example of this and we're going to do it in detail. Okay, so first off, use left and right endpoints to find two approximations of the area of the region. So we're gonna find two approximations. We're gonna find a lower and an upper sum. Between the graph of, so we're looking for the area of the region between the graph of f of x equals x squared and the x-axis over the interval 0 to 2. So the region, and I put the graph here. Generally, like you're not always going to be given the graph. You want to be able to think about it algebraically as well. But I wanted you to see the connections here between the graph and the algebraic method. So all that this is saying is we have our function, we have the x-axis, and then between 0 and 2. And so that gives us the region that we're trying to find the area of. So you always want to know what your region is. And then this is telling us how many subintervals. So I like to start off with finding the size of the intervals. So remember we had that formula on the previous page. Delta x is b minus a over n. And in this case, we're looking at the interval a to b, 0 to 2, and n is going to be 4 because that's how many intervals. So we're getting 2 minus 0 over 4, which is 1/2. Okay, so that is the size of the intervals. So how I like to do this is I like to write out what my intervals are. So remember we're starting at 0 and they each should be a size of 1/2. So it's going to be one interval 0 to 1/2. The next one is 1/2 to 1. It can also be helpful to keep everything with a common denominator. So I'm going to do that. Instead of writing 1, I'm going to write 2 over 2. And then we have 2 over 2 to 3 over 2. And then finally 3 over 2 to 4 over 2, should always double check that you're ending in the right spot. So we have 4 intervals and we are ending at 2, which is where we wanted to end. 4 over 2 is 2. Okay, and here's another important thing. Well, maybe I should say that at the end. I'll say that after. Okay, so let's use, we'll do, this one's going to be the left endpoints, and for this one we'll do the right endpoints. So let's just think about this. So the left endpoints of my intervals, so this is my 1/2, this is my 2 over 2, this is my 3 over 2, and then I already have my 2 there. The left endpoints are going to be 0. That's the left endpoint of the 0 to 1/2. So if I make a rectangle here, it's not a rectangle, it's a flat line. Okay, then I have this left endpoint, and I'm going to make my rectangle using that height. Then for my next one, I again have my left endpoint, and I am using that for my height. And then finally, I have this one, and I am using that for my height. And so this is what I am getting. And notice that so this is the point f of 0, this y value, f of 1/2, f of 2 over 2, and f of 3 over 2. Those are those y values. And so you can see here that we're ending up with an under approximation, so this ends up being a lower sum. The reason it ends up being a lower sum is because our function is increasing. Since f is increasing, the left endpoint is the minimum value on the interval, right? Because it's always getting bigger as we move to the right. So the converse of that is that the right endpoint will be the maximum value. Okay, so here we go. We can write this out using, I just want to show you how to do it using the notation. So this is the lower sum, so I'm going to use the lowercase s. Formula is this. And so remember, the delta x is a constant, so I'm going to factor that out. Front, it's not really factor, you can move it out front. Okay, and so this is what we're going to end up with. In this case, n is 4. So we're going to have s of 4 equals delta x we found earlier, that was 1/2, that's the size of the interval. And then for the sum, I'm just going to write it out already. It's going to be f of each of our minimum points, right? So f of 0, f of 1/2, f of 2 over 2, f of 3 over 2. And then find each of those. The function was x squared, so f of 0 will be 0 squared. This one will be 1/2 squared. This one will be 2 over 2 squared, and this one will be 3 over 2 squared. And then keep going. We have 1/2, we have 0 plus 1/4 plus 4 over 4 plus 9 over 4. This is why I like to keep the common denominator so that I don't have to find it later on. Add those up, 9, 10, 11, 12, 13, 14 over 4 times 1/2 would be 14 over 8, which you could simplify, of course, to 7 over 4. And so that is the lower sum. And then you can do the upper sum. And so here we're using the right endpoints end up being the upper sum. So right endpoint, draw your rectangle. Right endpoint, draw your rectangle. So the right endpoint is ending up as the height of the rectangle. And now you can see that we're going to end up over approximating. And so this is capital S of n, capital M. Again, you can bring that delta x out. So I'm going to skip writing this. We're going to go to S of 4, capital S, is going to be delta x, which is 1/2. And now we're finding f of all of our right endpoints. So this is going to be f of 1/2 plus f of 2/2 plus f of 3/2 plus, oh geez, f of 4/2. Sorry, should have scooted over. So remember, because this is 1/2, 2/2, 3/2, and then 2. So this is going to be 1/2 squared plus 2/2 squared plus 3/2 squared plus 4/2 squared. And that's going to be 1/4 plus 4/4 plus 9/4 plus 16/4. Add those up and you get 10, 20, 30/4. And so we are getting 30/8, which would be 15/4. So this is our over approximation. Okay, and so I wanted to include these. You don't need these in the homework today, these theorems in the boxes, but I just wanted to show what it's saying is that as n is approaching infinity, so the more and more intervals you have, right? Imagine like they're getting smaller and smaller and smaller and smaller and smaller. And as those intervals get tiny, because you have so many of them, the upper and the lower sums will end up equaling each other. The lower sum will equal the upper sum. So that's what that's saying. If those get like, if you have infinitely many subintervals, they would become equal. And so you don't really have to worry about this one right now. We're going to continue working with this idea a bit next class, but this should get you through the homework assignment. As always, let me know if you have any questions, and I will see you soon. Bye.